Welcome back, everybody, to yet another exciting day of statistics. And today we're continuing with Chapter 6, my favorite chapter, probability. And today we're going to look at probability models. Okay. So these are things you should already be familiar with, but I'm going to just make sure you are. When you are doing a probability problem, creating a sample space can be very useful. We did that last time. But here's an example. We talked about a deck of cards last time as well. So those of you that were having trouble understanding what's in a deck of cards, here you go. This would be the sample space for a standard deck of cards. Okay, and then you could use this to circle things, cross things out, count things, etc. Okay, so that's a sample space. It's just listing all the possible outcomes. Okay, now, once you start having multiple events, creating a tree diagram can be very useful. Realize the tree diagram can also be a replacement of a sample space. So for example, here, flipping a coin and rolling a standard die. I can go the coin heads or tails, and then once that occurs, I have my die 1 through 6, 1 through 6. Okay, I could give this same information as a sample space, right? Heads 1, heads 2, heads 3, and so on, right? All the way out till tails 6. And I would list out 12 things in this sample space. Here are the same 12, right? They're the 12 branches of my tree diagram. Now, the nice thing about the tree diagram is you can multiply your way down these branches to find the probability. So if you say, oh, what's the probability my coin lands on heads and my die lands on 6, I would go, okay, 1/2 times 1/6, it's 1/12. Okay. Now, with my sample space, I would list all 12 outcomes out, and all 12 would be equally likely. So again, I could say 1 out of 12. But what's interesting about the tree diagram is sometimes not every outcome is equally likely. And then that allows me to put fractions that are unequal. And then as I work my way down the branches, I can multiply these fractions to get to my probability. So both are very useful, sample spaces and tree diagrams. But certain problems, I would say the tree diagram is quite useful because of if certain events are not equally likely. Okay, another one, I mentioned this last time, is the fundamental counting principle. Okay, so if we have a certain number of ways one event can occur and then a certain number of ways another event can occur, then I can find the total size of my sample space by simply multiplying the two, right? So a coin has 2 possible outcomes. This die has 6. 2 times 6 is 12, right? And you can see visually that's why they multiply, because when you make the tree diagram, you keep branching off and you keep adding that many branches to the previous branches. So fundamental counting principle, very handy. Okay, now here's where things just start to get a little bit tricky for students. It's very important when you're doing a probability question to pay attention if items are being replaced or not. So here's an example. Let's say I have these 5 marbles and I'm going to randomly pick a marble. Well, first of all, notice there are 3 red and 2 blue. So the probability of red versus blue is not equal. And so that's why making this tree diagram is quite helpful. I can say, there's a 2/5 chance of blue. There's a 3/5 chance of red. And then I can work my way down. My next selection, if I do not replace this way, I would only have 1 blue left, but still have the 3 reds. So the next marble would be 1 in 4 of being blue, 3 out of 4 of being red. But if I take this branch, you can see it changes, right? This branch, I took out a red, so I now have 2 blue, 2 red, so they're both 2 out of 4. And so on and so forth as I work my way down the branches of my tree diagram. So this is an excellent example of where a tree diagram can come in handy because our by not having any replacement, this is an example of no replacement, I can adjust as I go and keep track of the outcomes. And so, for example, right here, if somebody said, okay, what's the probability if you draw 2 marbles without replacement? What's the probability they're both blue? 2/5 times 1/4, there it is. Right? You just multiply right down the branches. What's the probability they're both red? 3/5 times 2/4, and there you go. So on and so forth. And if you multiply all of the branches out, you can have the entire distribution of outcomes listed right here, which is very handy. And then you can add them all up and make sure they add to 1, right? If you leave them as fractions, you haven't rounded, and all the fractions will, of course, have a sum of exactly 1, unless you've made a mistake. Okay, a little bit of vocabulary. I've already used this word quite a bit. An event, right? So an event. So that can be, oh, the event is drawing a blue marble, right? There you go. That could be an event. Or it could be a group of outcomes. I could say, well, what's the probability of the event that I draw 2 red marbles, right? So it could be a single outcome, or it could be a group of outcomes. All right, some basic rules. Again, you should already kind of know this, right? We mentioned last time the lowest possible probability is 0. Something cannot happen a negative number of times because probability is a ratio of 2 counts. And the greatest possible probability is exactly 1, or 100%. Again, we mentioned that last time. So probability ranges from 0 to 1, 0 being impossible, although sometimes we will assign an event a probability of 0 that could happen. We mentioned that with an example last time. Okay, all the way out to a sure thing, a certainty. Again, we could assign something a probability of 1 that isn't technically a guarantee. We went over that last time as well. Okay, and then just some kind of basic vocabulary, things that are over here, 5%, 10% chance. We say that's pretty unlikely. Okay, flipping a coin, that's called an even chance, right? 50-50. Things that happen fairly frequently, we say, oh, it's pretty likely to happen. Okay, so just kind of the way words work with this interval. Okay, now here's something you may or may not know. You probably know it from a common sense approach, but you may or may not know the notation and the word complementary events. So complementary events are, well, let me give you an example. Let's say the probability that it rains today, probably we get any rain, is 10%. Okay? And I'm giving you that information. That's a given. Now I'm going to ask you a question. What's the probability that we get no rain today? Notice I don't need to tell you that. And you can very simply just say, oh, well, if there's a 10% chance of rain, then the chance that it doesn't rain is 1 minus 0.1, or 100% minus 10%. 90% chance that it doesn't rain. Okay, that concept, that's complementary events. Raining and not raining are complementary. It has to do one or the other. Well, I mean, I guess there's snowing, but the idea here is complementary events cover the whole sample space, so their sum is 1. So for example, instead of rain, I could talk about test grades. What's the probability you get an A on chapter 6? Okay, let's say it is, I don't know, 0.8 or 80%. Okay, so then what's the probability not an A? Oh, well, there you go. It must be 20%, right? Because those are complementary. You either get an A or you don't get an A. And here's the notation we'll use for complementary events. So the probability of A complement, see, we use a superscript, right? An exponent of lowercase c, that's read A complement. Probability of A complement is simply equal to 1 minus the probability of A, right? So the probability of an event not occurring is equal to 1 minus the probability of the event occurring. And as complementary events. All right, here's some rules. A lot of students fall in love with these two rules and try to use them on every single problem. But it's very important to note. This is the addition rule for disjoint events. You may not use this for joint events. It only works for disjoint events. Okay? So if I say, what's the probability that event A or event B occurs? It's simply the union. It's simply probability of A plus probability of B. Notice, if there's anything here overlapping, this will be untrue, right? So this will only work when I have no overlap, right? When this C area is 0. And by the way, this is a Venn diagram. It's also very useful in probability. Okay, so this only works for disjoint events. For example, we did drawing a card from a deck last time, right? Draw one card from a standard deck. Okay, what's the probability? It is red or a club. Are there any red clubs? No. So these are disjoint events. There's no overlap. They cannot occur at the same time. So to do this, I could simply take the probability of red, which is 26 out of 52, plus the probability of getting a club, 13 out of 52. And there you go. That's using my rule for disjoint events. But you might remember last time I said, well, red or a jack, right? Now this doesn't work anymore because you'll be double counting the red jacks. So please, please, please pay attention if you have disjoint events versus joint events. If there's any overlap, it's called joint. If there's no overlap, it's called disjoint. Okay, the other rule today is the multiplication rule for independent events. Again, this is a rule that only works under the condition of independent events. It doesn't work if you have dependent events. And I think this is the most commonly messed up rule on the test. For some reason, students like to think everything is independent, when in fact, lots of things are dependent. Okay? So when you have independent events, their intersection, right, or the probability of both events occurring, simply the multiplication of their probabilities. Okay, again, if you have independent events. Let's talk about what makes independent events. If you are drawing or taking multiple selections, to have independence, you have to replace and remix between selections. That's simple. So if we go back to our marble example, right? Here, I have no replacement. So this is dependent. You see how the probabilities change depending on what's been removed. Okay, that's dependent. I could not use this rule, this multiplication rule, on a problem like that. Okay, when you talk about cards and you're playing a game of cards where cards are being dealt, that's dependent. We can no longer use this rule. Okay, so again, this rule only works for independent events. That would be something like our example here. Whatever the coin lands on has no impact on what the die lands on. Okay, those are independent. The coin has no effect, no impact. Okay, but once you have something where your first item or action impacts the chances of the next, then you have dependence. Okay. All right. And by the way, actually, no. I'm not sure if these are on your formula sheet or not, but I know that the important ones that we're going to learn next lesson are on your formula sheet. So it's really not hugely important to know these because we'll learn rules that always work next time. So I just would focus on learning the rules that always work for every situation. All right, let's try an example. We'll start here. Let's start simple. All right, so let's say there's a group of friends, Leon, Frank, and Paula. And they're gonna play doubles tennis. Oh, and for Ray is also in this group. Okay, so let's say that the probability that Leon asks Frank to be his tennis partner is 1/4. So here's what I'm gonna do. I'm gonna say, okay, the probability of Leon asking is 1/4. Okay, probability that Paula will ask Frank is 1/3. Okay, so probability of Paula is 1/3. Probability that Ray will ask Frank is 3/4. All right, probability of Ray asking is 3/4. Okay, now really important. This problem is stating, let's assume there's independence. It's probably a poor assumption, right? These people probably are friends and talk to each other, and they would already say, oh yeah, Frank agreed to be my tennis partner, and so then that would end it. But we're pretending that it is independent. All right, so here's our question. What's the probability Paula will ask and Leon will ask? Well, if I can assume independence, right, the probability Paula and Leon both asking, if I have independence, which it says, is simply the probability of Paula times the probability of Leon. Okay, and again, that's only because we said independence. Okay, so let's work that out. That is 1/3 times 1/4. So 1 in 12 chance that they both ask. Okay. All right, now let's try another one. This one's going to be a little more challenging. What's the probability that Ray and Paula both ask, but Leon does not ask? Okay, so I want to find the probability Ray and Paula ask and Leon does not ask, right? That's the complement of Leon asking, because he's either going to ask or he's not going to ask, right? They're complementary events. Okay, notice the problem didn't give us the complement, but we know the complement of 1/4 is 3/4. There's a 3/4 chance Leon will not ask. Okay, so Ray asking is 3/4. Paula asking is 1/3. Leon not asking will be 3/4. Okay, if you want, you can reduce as you go. Sometimes I like to leave it in a non-simplified state because there might be some future problems dealing with this situation. And then if I have not reduced, I'll have common denominators that I can very quickly use. So I like to do it not reduced and then, also reduced. All right, so what is that? 1248. Okay, and then, if you want to reduce it now, go for it or not. Okay. All right, now I have some more questions dealing with this scenario. Here's where it gets harder. Once you start seeing things like at least, at most, now you have multiple outcomes that will work. So you have to find the probability of each of the outcomes, and then you can add them together. So what's the probability at least 2 of the 3? Okay, I'm going to again put the information up here. Okay, at least 2 out of 3. Well, here's what I'm going to do. I'm going to try to explain what that means. At least 2 out of 3. So probability at least 2. Okay, well, at least 2. For me, that means I could say, well, that's the probability of exactly 2 asking, or the probability of exactly 3 asking. Right? At least 2. That means exactly 2 or more, right? In this case, the or more stops at 3 because that's all we could have. All right, so I now know that it's the sum of these 2 probabilities. Now, exactly 2 asking, there's multiple ways that that could happen. So let's break that down. Okay, that could be Leon and Paula, but not Ray. It could be Leon, not Paula, but Ray does. Or it could be Leon's the one that doesn't ask, but Paula and Ray do. Okay, so there's 3 ways that exactly 2 people can ask. Let's calculate them. So let's see, Leon and Paula ask, but Ray doesn't ask. So the complement here would be 1/4. Okay, let's see, this one is Leon asks, Paula does not, so the complement to Paula. Ray does ask. All right, this one is Leon does not ask, so the complement of that is 3/4. And then Paula asks, and Ray asks. Okay, so this calculation right here will give me the probability that exactly 2 ask Ray to be his tennis partner. Let's work it out. So that is 1 out of 48, 6 out of 48. And you can see why I was saying if you just leave the denominator as 48, when you start adding things, you have a common denominator. All right, so that is what, 16 out of 48. That's the chances that exactly 2 of them ask. So if the problem said, what's the probability exactly 2 ask? Well, there you go, you'd be done, but that's not what it said. It said at least 2, so I'm still not done. I still have to figure out exactly 3 and add it to this. So let's do the probability of exactly 3. Well, this is much easier. There's only one way that can happen, right? All 3 ask. So all right, so that is 1/4 times 1/3 times 3/4. Or in other words, 3 out of 48. And so now we can answer the question. Exactly 2 plus exactly 3. So our answer is 19 out of 48. Okay, and this is where, again, it gets a little tricky for students. They have trouble listing out all of the acceptable outcomes. And then they don't count everything. And if you don't count everything, you get the problem wrong. So that's the key. Again, I mentioned counting would prove difficult. So be careful, take your time, and make sure you list out every outcome that is acceptable, and then count that outcome exactly once. All right, let's try another one. Let's find the probability that at least one of the 3 friends ask. Okay, so again, let me copy down the basic info. All right, probability at least 1. Well, that would be the probability of exactly 1 would work. Probability of exactly 2. Or exactly 3. All of those would meet the criteria of at least 1. Now here's the good news. We've already calculated these 2, so let's just calculate the exactly 1, and then we can answer the question. So probability of exactly 1, well, it could be that only Leon. So that would be Leon asks, Paula doesn't, Ray doesn't. Okay. Or it could be that it was just Paula. So Leon does not, Paula does, Ray does not. Or it could be that it's just Ray. So those are the three ways that exactly one person could ask. Well, let's work them out. So that would be 1/4. Paula not asking is 2/3. Ray not asking is 1/4. All right, Leon not asking is 3/4. Paula asking is 1/3. Ray not asking is 1/4. And lastly, Leon not asking, 3/4. Paula not asking, 2/3. Ray asking, 3/4. There's the most likely outcome of any of the outcomes in the sample space, right? Okay, work this out. 2 out of 48, 3 out of 48, 18 out of 48. So 23 out of 48, there's the chance that exactly one asks. And again, that would have been a fair question too, right? I could have said, what's the probability exactly one of the three asks? There's the answer to that. All right, but now the question was at least one. So that would be exactly 1 plus exactly 2, which we had earlier as 16 out of 48, plus all three asking. And there we go. So what is that, 42? Now, could I have answered this question in an easier manner? Yes, I could, right? The complement. What's the complement of at least 1? Yeah, the complement there would be none. So I could have said the probability of at least 1 is equal to 1 minus the probability of none. That would have been the fast way to do this problem. So that's 1 minus probability of none. That would be all complements, right? Leon complement, Paula complement, Ray complement. So that is 3/4 times 2/3 times 1/4. That is 1 minus 6 out of 48, which is 42 out of 48. Bingo. Now, personally, I like to do both. And then when they're equal, I get to say yes. That's my check. Okay. And another thing I really like to do is calculate everything in the entire sample space, which we have now done. We went everywhere from none all the way up to all three, and we can see that their sum, if I add all those together, would be exactly 1. So there's another check. I've completed the entire sample space, and the sum of my sample space is exactly 1. So that, again, confirms that I've done the problem correctly. Okay, so when you have time, do that. Do things in the straightforward way, and then do things using the complement, and then fill in the entire sample space. Make sure that it has a sum of 1. So now I can be very confident that it's right. Okay, and there we are. All right. One more problem. Let's say you are playing poker, one of my favorite games. But you're just playing 5-card poker as opposed to, say, Texas Hold'em. So you're playing, 5-card stud or something along those lines. What's the probability you are dealt a royal flush? That is the best hand in poker. It cannot lose, assuming you're not playing wild cards, which in my opinion isn't poker. Okay, so you're playing traditional poker, no wild cards, and you want that royal flush. What's the probability of being dealt it if you're only receiving 5 cards? Okay, a royal flush is an ace, king, queen, jack, 10, all in one suit. Doesn't matter which suit, it can be any suit. Okay? And for those of you that don't know how poker works, it doesn't matter what order you are dealt these 5 cards. They could come to you in any order. All that matters is that you possess these 5 cards and that they are all in the same suit. So pause the video and give this problem a shot. Okay, here's the way I'd probably do the problem right now, since we haven't talked about combinations, permutations, and all that fun stuff. If you have talked about those in previous math classes, go ahead and use that. It will save you some time. I'm going to just kind of use a common sense approach using my various rules. All right, so you have no cards. The very first card that comes your way, you would be willing to accept any ace, any king, any queen, any jack, any 10. Doesn't matter the suit on the very first card that you get, right? So that means there are 1, 2, 3, 4, 5 cards, but of any of the 4 suits. So there are 20 cards out of the 52 that would be acceptable for your first card. Okay. Now, the next card, you've received one of these 5 cards and your suit has now been chosen for you, right? Because the next card will have to match the suit of the first card. So that means there will only be 4 cards that are acceptable left in that deck. And there will only be 51 cards left in the deck because you possess one. Okay? And then continuing on, you now possess 2 of these 5 cards. So there's only 3 left, and there's only 50 left in the deck. Continuing on, 2 out of 49. And then your last card will have a 1 in 48 chance of completing your royal flush. There you go. That's the chances of being dealt a royal flush if you're playing 5-card poker. If you're playing 7-card poker, we really want to get into combinations because it does start to get pretty complicated. And we'll talk about that a little bit more next time. By the way, some people will do this problem this way. They'll say, okay, let's say I want to get a royal flush in hearts. And they'd go, okay, so any of those 5 out of 52, and then, right, they would get this, and then they'd go, okay, now there are 4 acceptable suits, so multiply that by 4. You'll notice it's the same thing, same answer. Okay, but those of you that have had combinations, you'll notice that, hey, 5, 4, 3, 2, 1, 52, 51, 50, 49, 48, right? These are partial factorials, which of course that's what combinations do. So that's why I was mentioning you could use combinations on this and save yourself a little bit of work, but that one wasn't too complicated because we needed all 5 of those cards to be very specific cards. If we do this problem again for like a 7-card hand, it becomes a little bit more challenging, and that's where combinations would become quite helpful. Okay, hopefully you like probability as much as I do, and enjoy. We'll be back again for one more lesson in probability for 6.3. Have a good day.